To begin this lesson, let's bring back our 52 playing cards as you see from the graphic right here. What I'm going to do is I'm going to set up a scenario of picking a card. If you look right below here, what I have is someone fanning out a deck and then somebody else picking a card. We're going to call this event E, picking a card. Okay, from there, what we're going to do is there are two different options. We'll start with our upper option. We're going to, let's say in this scenario, return the card to the deck. In the world of probability, we call that with replacement. So what's going to happen is the jack is going to go back into our deck here, and we're back to 52 cards. Think of it as refreshing the deck. If we then go to pick another card, so this is the first scenario in which we're doing multiple events in a row. Let's say we pick a second card. So the main concept that we have to figure out here is whether picking the first card has any probabilistic effect on picking the second card. Well, if we put the card back in and refresh that deck, then that means it doesn't. So we would say in this context that the events E and F are independent. So that is our keyword here, independent. Okay, so now let's go the other route. So let's just say, again, we end up picking a card from a 52 card deck. You're holding and looking at that card, and instead of putting it back in the deck like the previous option, we decide to keep the card. In the world of probability, this is called without replacement. Okay, so this creates a little bit of a change in the scenario. Why? If you don't put the card back in the deck, that means we go from 52 cards to only 51. So when we go to pick the second card, event F, we now have a different denominator for our probability because the sample space has changed. So what does this mean? This means that in picking the first card, it has affected the probability of picking the second card. So therefore, we would say that E and F are now dependent. In understanding the concept of independent versus dependent events, that allows us to move on to our next rule called the multiplication rule. Now you can see down here, I've already written it. The multiplication rule for this section is going to concentrate just on independent events. We will talk about the dependent event scenario in a later section. But for now, what does the multiplication rule look like for independent events? It looks just like this. If we are choosing to pick, let's say in this scenario, two cards in succession, then we would say the probability of event E and then event F is going to be equal to the product, or in other words, multiplying the individual probabilities of event E and event F. Okay, suppose that you have played cards in your life. I could totally see a scenario where in the middle of a card game, let's say there's 52 cards out and somebody picks two jacks in a row. Maybe you think to yourself, man, how unlikely is that to happen, to get two jacks in a row? Well, that's the exact scenario that we're trying to hammer home with the multiplication rule. So let's literally pick that scenario, picking two jacks in succession. So in order to make this work, we're going to create the event. So event E is going to be picking the first jack. Event F is going to be picking the second jack. Now note, When we do this scenario, we're going to say with replacement, because right now the only multiplication rule that we know is one for independent events. And recall from our example up here, we have the independent events are based on having with replacement in terms of your probability experiment. So based on all of this, we should be able to find this probability. For example, if we want to find the probability of E, which is picking the first jack, the original deck has 52 cards. That is our sample space. We're looking for the event of picking a jack. Well, if you go to the playing cards at the top, you can clearly see by this column right here that there are 4 jacks in the deck. Therefore, our event would be 4 out of 52. We move on to the probability of F. The key thing here again is that these are independent events, which means there was replacement of the first jack. Once you put the first jack back in our deck over here, then we still have 52 cards. It has been refreshed, and we still have 4 jacks, which means if we calculate this, we're going to get 0.0059. So to answer that hypothetical person that's saying, how likely is it to pick 2 jacks in a row? Well, if you're replacing it, then it would be around 0.006 or 0.0059. Okay, let's look at another example. It says a bowl contains 4 red, 3 green, and 5 white cubes. Find the probability of selecting a white cube and a red cube with replacement. Okay, so what are we looking at here? We're looking for a scenario of with replacement, as you see right here, which means that this is another way of saying that the events in this are going to be independent of one another. Well, what are the events? The events were selecting a white cube right here, which we will call W, the event W, and selecting a red cube. So we'll say event R. Since it appears that we are picking these 2 cubes in succession, then we can use the multiplication rule of independent events. So the probability of W and R should be equal to this product of the individual probabilities. So how do we find out these individual probabilities? Well, we start with the fact that we have 4 plus 3 plus 5 equals 12 total cubes. So therefore, we're going to have 12 in our sample space when we first reach in that bowl to get a cube. And what is the event of getting a white? Well, there's 5 opportunities for that. Now, because we have replacement, we're going to take that white cube, we're going to put it back in the bowl, and it's going to refresh the bowl to 12 cubes. So when we go in to pick the red cube on the second dig into the bowl, there's going to be 12 again, but we're looking for red this time. The event of red is 4. So we're going to get 5/12 times 4/12, which is approximately 0.1389. One tiny bit of information that is very important in terms of the multiplication rule is that we're not limited to just 2 events. The reality is we could do 3 events, 5 events, 8 events, and the multiplication rule for independent events can be applied as is. Just as an example, just skipping back up to our 2 jacks example, let's say that we decided to make event G be picking the third jack. The third jack. So what does that mean for us? Well, what if we want to pick 3 jacks in succession with replacement? Well, let's look at our formula. Well, we would start with the probability of E, and then F, and then G. So it looks a little bit different than our original, but it's just an extension, which would be, if they're independent events, literally the product of all the events themselves, individual events. So if that's true, and we are returning every single time to the deck, then we're going to get 4 out of 52 times 4 out of 52 times 4 out of 52, which is going to be equal to something. You can do that later. The key is that understanding is that this rule can be applied to multiple events beyond just 2. Okay, let's look at an example. It says the probability that a randomly selected 24-year-old male will survive the year is 0.9986, according to the National Vital Statistics Report, what is the probability that 3 randomly selected 24-year-old males will survive the year? Okay, seems a little dreaded, but this is something that insurance companies will use, specifically life insurance companies. So definitely a common statistical application in a real-world setting if you're in life insurance. So what are we looking at here? Well, remember, we're looking at survive the year as an event. So we will call that E. Now, according to this, there are 3 males that are going to survive the year. So just to do something a little different, to give you a nice creative way of doing things, instead of doing different letters for the events, I'm going to use subscripts. So if there's 3 males, we're going to use the event E1, E2, and E3. So just subscripts that label the survival of 3 different males. So how would we find this probability? Well, we're looking for the probability that the first person survives, and then the second person, specifically a male, survives, and then the third person survives. 3 in succession. So therefore, that should be equal to, if these are independent events, the probability of E1 times the probability of E2 times the probability of E3. Now, a student might ask, well, are they independent events? Because there was no mention of replacement anywhere. Well, there is no replacement in this scenario. Sometimes you have to judge independence based on the actual thing happening. And in this case, is the survival of one person based on some other randomly or affecting some other randomly chosen male? It really isn't. They don't have probabilistic effect on each other, which means we would say each of these male survival are independent of one another, which allows us to use this rule. So what does that mean for us? Well, they told you that the probability of any one male surviving is 0.9986. which means this probability is going to be 0.9986. And this probability is going to be the same. So is this probability. So we could absolutely put these numbers into the calculator. There's no problem with doing so. But we could also do this a little bit in a short way, let's say, by simply saying this is the same as 0.9986 to the third. That's a little bit easier to calculate in your calculator, so, or at least shorter. So if you do this, you're going to get about 0.9958 as your probability. Okay, so what if we went on to do 20 randomly selected 24-year-old males and how they would survive? Well, we would obviously need E1, E2, E3 again, but we would have to go all the way to E20. We clearly don't want to write this thing out for E1 to E20. That sounds insanity. So instead of doing so, let's just be logical about this, right? Here, we had 3 of these males surviving at 0.9986, and it ended up being 0.9986 to the third. So if we have 20 of them, then it should be 0.9986 to the 20th. So that's going to be a little bit different in terms of probability, but not too much. You're going to end up with 0.9724 as your result, which is a little lower probability, and that makes a lot of sense in terms of the fact that you have 20 instead of 3 people.